beginning of the year, we learned about linear functions. And linear functions have one x to a power of 1. And we know that when we graph a linear function, it looks like a line. That slope can be changed, but we know that the line will go either up or down or straight across or vertical. Then in chapter 9, we talked about when we have an x squared term, and that will change our graph. Our graph will now look like a parabola, and that parabola can face up or down. It has a vertex and axis of symmetry, but whenever we have an x squared in our function, it's going to be shaped like a parabola. What happens now if we put the x in the exponent? So if we have a number being raised to the x, what shape will that graph take when we graph it? Let's take a look at y equals 3 to the x. The shape of this graph is kind of interesting. If you trace along it, we'll see that in the negative x's, when x is a negative exponent, it will be really close to 0 on the y, but it will never actually touch it. If we zoom in, we'll notice that it never actually touches the x-axis, but it does get really forever close to it for infinity. And then as we get bigger on the x, it gets exponentially bigger on the y, and it keeps going up forever and ever in that y direction. Now let's take a look for a minute at what happens if our base of the exponent is not a number that is bigger than 1, but is instead a number that is between 0 and 1, or a fraction, or a decimal. How will that change our graph? Let's keep both of them on there. So the blue one is the first one that we graphed, and the red one is our new one. Take a look at the difference. Our blue one is when we had a number that is bigger than 1 as the base of our exponent. And then the red graph is when we have a decimal as the base of our exponent. These are both exponential functions, but the blue one we call exponential growth because as we slide to the right, the function grows and the y value gets bigger and bigger and bigger and bigger in infinity. And we call the red one, where the a value or the base of the exponent is a fraction or a decimal, we call this exponential decay, because as we slide from left to right, the graph gets closer and closer and closer to 0 on the x-axis, but it never actually reaches it. Notice that out here at x equals 15, the y value is 2.9 times 10 to the negative fifth, scientific notation, so a very, very, very small number. Now let's take a look and see what happens if we place a number in front. Compare these two with the two green pluses. I have y equals 3 to the x up here, and then right here I have y equals 2 times 3 to the x. So I have a coefficient, I have a number in front of the exponent. How will that change our graph? Let's graph both of those. Blue is our original and green is our new. Notice that blue is that y equals 3 to the x, and green is that 2 times 3 to the x. And notice that the green just climbs up a little bit faster. It gets numbers, y values bigger, because when you multiply your answer each time by 2, it grows a lot faster. Now likewise, let's compare what happens if we multiply 2 times our exponential decay, when that a value or that base value is a fraction. Let's take a look here. Notice that our original is the red, and when we multiply our answers each time by 2, we're sticking that 2 into the equation, it just decays down a little bit slower, okay? So notice that that value changes the graph. We won't get too much into detail with that, but what I want you to focus on is the fact that exponential growth and exponential decay are going to have graphs that look like this. Exponential growth slides up from left to right, and that's when a number or a value of the base of the exponent is greater than 1. And when we have it, the base being less than 1, being a fraction or a decimal, but still greater than 0, we have exponential decay. if we had that base actually equaling to 1, it would no longer be an exponential function. Watch this. If I just have 1 to the x, and if that's the only one I graph, notice it's just a straight line. Y equals 1. So it loses that exponential graph feature if it's a 1 in that base right there. So it has to either be a number greater than 1, like 3, or a decimal, like 0.5 or 0.25, 1/2, 1/4, to get that exponential shape. Notice I summarized this on your note sheet. Today we're learning to graph exponential functions. In this type of function, the variable appears as an exponent. The value that's in front being multiplied, like that coefficient, cannot equal 0, otherwise the whole thing would equal 0. And the number that's being raised to the power cannot equal 1, otherwise it's just a straight line like I showed you. It has to be bigger than 0. Now, if it's between 0 and 1, the fraction, then it has the shape of the exponential decay. And if it's between 1 and going forward, bigger than 1, then we know we have that exponential growth. Looking at our first example, the function f of x equals 1500 times 0.995 to the x power is an exponential function because the x is in the exponent. Notice that the value that's being raised to the x is a decimal or a fraction, a number between 0 and 1. So that's going to be somewhere between 0 and 1. This is going to be exponential decay. So modeling this prairie dog population, we're going to have our prairie dogs actually getting fewer and fewer and fewer as time goes on. Our prairie dogs are they're dying out. We want to know how many prairie dogs will there be after 8 years. To determine this, we simply plug in 8 for our x and use a calculator to help us determine the answer. Now, when we simplify these, we're going to do the piece raised to the exponent first. Remember, PEMDAS, order of operations, and then multiply times 1500. 0.995 to the 8th is 0.96. Now I'm going to multiply that times 1500, and that gives us 1,441. I am not going to include the 0.04 onto my answer because you can't have 4/100ths of a prairie dog. So we have approximately 1,441 prairie dogs left after they decay or after they decrease for 8 years. Our second example talks about a model for width of a photograph in inches after it has been reduced by 25% a certain number of times, meaning you reduce the picture by 25% one time, and then a second time, and then a third time, and then a fourth time, and so on. What's the width of the photograph after it's been reduced 3 times? So we're going to plug that 3 in for x. Remember that p of 0.75 is just a fancy way of saying I'm plugging 0.75 everywhere there's an x in this equation. Now remember, I do my 0.75 cubed first, and then I multiply my answer times 8. And 8 times 0.42 is 3.375. And it's what's the width in inches, it looks like. So 3.375 inches would be the final width of that photograph. All right, now we're talking about completing a table to be graphing this type of a shape, exponential decay or exponential growth, using a t-table. When we do that, we're going to plug in the values for x in for x. I did that over here. Notice I keep everything the same and plug in my 1, 2, 3, 4 in place of that x. Now, just like above, order of operations says we need to do the exponent before we multiply. So in this first case, 3 to the 1 would be 3, and then multiply 2 would be 6. 3 to the 2 would be 9, and then multiply 2, which would be 18. 3 cubed is 27, and then multiply times 2, which would be 54. And finally, 3 to the 4th multiplied by 2 would equal 162 total. Now there is a pattern to this t-table. Do you guys remember with linear, we would multiply, or excuse me, we would add the same thing to each row and it would work out with a pattern. With quadratic, do you remember the second differences were common? Well, with an exponential, it has to do with multiplying. So notice if I multiply 6 times 3, that gives me 18. 18 times 3 gives me 54, and 54 times 3 gives me 162. So as long as the x's are going up by a constant amount, by 1 each time, the y values are multiplied by a constant amount. Let's talk about graphing now. All right, if I'm given an exponential function, remember I know it's exponential because it's being raised to a power that has an x. To graph it, I can make a t-table. I write out my function and I put in values -2 through 2, would give me a good kind of range to play with it a little bit. And I plug each of those values in for x. To save time on the video, I'm going to go ahead and do it for you. However, notice that I'm always doing the exponent first, 2 to the -2, and then multiplying by 3. When you plug this into your calculator, make sure you use parentheses, 2 to the -2 power, get enter, get your answer, and then multiply by 3. I'm going to go ahead and do a few, check it, and see if you get the same answers as me. All right, these are the answers that I got when I simplified. Now I'm going to plot each of the points just like we do for t-tables. Check and see what it will look like. Well, actually, before I do, notice that the base for the exponent is a number between 0 and 1. So is this going to be exponential growth or exponential decay? Because it is a number bigger than 1, it's going to be exponential growth. So it should look something like this. Let's see what it looks like. Plotting my dots, I get this. And I will go ahead and connect them through. And this would be my graph. Let's look at this one next. I'm going to make a t-table. I plugged in my numbers. I picked some negatives, a 0, and some positives. I plugged in those values for x. And these are our outputs. We're going to put them on the graph, but before I do, I'm going to predict if this number that is being raised to the x is a fraction or a decimal or a number between 0 and 1, is this going to be exponential growth or exponential decay? Let's see if your prediction is right. If you predicted exponential decay, good job. And this is what our graph will look like. Now, kind of a cool feature, notice that the y-intercept on these graphs is equal to when x is 0. And remember, anything to a 0 power is just 1, making the coefficient being our y-intercept. So in this case, the coefficient 3 is our y-intercept because 2 to the 0 is just 1 times 3 is 3. And in this case, our coefficient is also 3. And our y-intercept is 3. So just kind of a cool thing you can kind of tell right from looking at it. This one will be exponential growth going through a y-intercept of 3. This one will be exponential decay with a y-intercept of 3. Now, do you remember when we did parabolas, what did the -a coefficient mean? Well, it meant that our parabola flipped upside down. And the same thing is going to happen with these exponential functions. So this shape is going to be flipped upside down if the initial coefficient is negative. Let's see what I mean. First off, let's say what we know. We know that the base is a number bigger than 1. So this is going to be exponential growth. We also know that because the initial coefficient is negative, that this is going to be flipped upside down. What is growth flipped upside down look like? That's growth. This is growth upside down. That's the shape we're going to get generally. Let's see what it looks like. I plotted my points and the graph looks like this. Notice especially that our y-intercept, where it crosses the y-axis, is at -5, and that is our coefficient value, because when x equals 0, this turns to 1, and -5 is the point where it will cross our y-axis. All right, let's take a look at our very last one. Finish up with this one. I'm going to see what I know about the graph. The point 4 is the base of the exponent. That number is between 0 and 1, which means this is going to be exponential decay. However, I notice that the coefficient is negative, which means it's going to be decay flipped upside down. Well, we know that the shape for decay looks like this, so flipping it upside down is going to look something like this. Let's check. I plotted my points, plugging in these numbers for x, and these were the points I got. Connecting the dots, I see that sure enough, this is the shape for my graph. And again, notice this y-intercept right here. When I plug in 0 for x, this piece turns to 1, and it's just y equals -2. So that y-intercept is -2, which is the same as that first coefficient. So we'll sum it up real quick before we go. If my b value is bigger than 1, then the graph is exponential growth. And if my value for the base of the exponent is between 0 and 1, then the graph is exponential decay.